Have you ever looked up at the moon, that glowing orb in the night sky, and let your imagination wander? For centuries, people have gazed upward, dreaming about what it would be like to set foot on its surface, to call it home, or even to build a new world there. Imagine waking up on the moon, stepping outside your habitat, and seeing Earth, a beautiful blue marble, hanging in the blackness, surrounded by a sky full of stars. The silence, the vastness, and the sense of adventure would be unlike anything on Earth. A sky full of stars, Earth glowing in the distance. It's a view that has inspired poets, scientists, and dreamers alike. But turning this dream into reality is a challenge that requires more than just imagination. But living on the moon isn't as simple as packing a bag and hopping on a rocket. It takes years of preparation, rigorous training, and the development of technology that can withstand the harsh lunar environment. The biggest question: how do you power a home, a lab, or a rover nearly 240,000 miles from Earth? Unlike Earth, the moon has no power grid, no gas stations, and no easy way to get supplies. Every watt of energy must be generated and managed on-site. NASA's answer: build a nuclear reactor on the moon. This isn't just a wild idea, it's a carefully engineered solution to one of space exploration's toughest problems. It sounds like science fiction, but it's quickly becoming reality. Teams of scientists and engineers are working around the clock, turning what once seemed impossible into the next giant leap for humanity. Astronauts will need power for life support, warmth during the freezing lunar night, and to run scientific instruments. Reliable energy will keep habitats livable, water flowing, and experiments running, even when the sun disappears for 2 weeks at a time. Why go to all this trouble? Because exploration is in our DNA. From crossing oceans to climbing mountains, humans have always pushed boundaries. The moon is the next frontier, calling us to test our limits and expand our horizons. The moon is our stepping stone to the cosmos, a place to develop the skills and tech for journeys even farther, maybe to Mars. By learning to live and work on the moon, we prepare ourselves for the challenges of deep space. But every great journey starts with a first step: securing a reliable energy source. Without power, even the most advanced technology is useless. That's why energy is the foundation of our lunar ambitions. That's where NASA's bold plan comes in. A lunar nuclear reactor could unlock our future on the moon. It would provide steady, long-lasting power, no matter how dark or cold it gets outside. It's a complex challenge, but the reward is a future where humans are no longer confined to one planet. We could build, explore, and thrive in places we once only dreamed about. And it all starts with a small, powerful reactor humming on the lunar surface, a beacon of human ingenuity, lighting the way for generations of explorers to come. The moon is a place of extremes: scorching days, freezing nights. Unlike Earth, which has a protective atmosphere and a relatively stable climate, the moon is exposed to the harshest conditions in the solar system. There's no air to buffer the temperature swings, and no clouds to shield the surface from the sun's relentless rays or the cold of space. When the sun shines, temperatures on the lunar surface soar above boiling, reaching up to 260 degrees Fahrenheit, hot enough to fry electronics and make survival outside a suit impossible. But when the sun sets, the situation reverses. Temperatures plunge to a bone-chilling minus 208 degrees Fahrenheit, colder than any place on Earth, turning the surface into a frozen wasteland. And lunar night? It's not just a few hours of darkness. It lasts 14 Earth days, 2 entire weeks where the sun never rises, plunging everything into darkness and deep cold. During this time, solar panels are rendered useless. They can't generate any electricity without sunlight, leaving habitats and equipment vulnerable. No sunlight means no electricity. Batteries can only store so much, and they drain quickly when powering life support and heating systems. Astronauts can't just wait for sunrise. They need continuous power for life support, warmth, and communication. Every system, from air filtration to water recycling, depends on a steady flow of energy. A power outage isn't just inconvenient, it's life-threatening. Without power, habitats freeze, oxygen runs out, and communication with Earth is lost. The margin for error is razor thin, but we want to do more than just survive. We want to conduct groundbreaking science, explore new frontiers, and tap into the moon's unique resources, mining ice for water and fuel, running advanced laboratories, and powering rovers for exploration. All these activities demand serious, reliable energy. Solar panels and batteries alone can't keep up with these demands, especially during the long lunar night. Energy shortages could halt missions and put lives at risk. That's why we need a power source that works day and night through searing heat and bitter cold. Something robust, dependable, and scalable. We need a system that can provide steady kilowatts for today's missions, and eventually megawatts for a thriving lunar community. The moon is unforgiving, and only the most reliable technology will do. To conquer it, we need unwavering energy. Power that never sleeps, no matter the conditions outside. This is the challenge NASA is determined to solve. Engineers and scientists are racing to develop new solutions, from compact nuclear reactors to advanced energy storage. Without a mighty power source, a permanent human presence on the moon is impossible. Our dreams of lunar cities and science outposts would remain just that, dreams. But with it, the moon becomes our gateway to the stars, a stepping stone for humanity's greatest adventures yet to come. Solar panels power the International Space Station and Mars rovers, but the moon is a different story. 14 days of darkness make solar power unreliable. To survive, a solar base would need massive, heavy batteries, impractical to launch from Earth. Enter nuclear power. A fission reactor doesn't care if it's day or night. It runs 24/7, providing steady power. No need for enormous batteries or sprawling solar farms. A compact reactor could power an entire outpost for years without refueling. Nuclear systems are power-dense, small, efficient, and long-lasting. It's not about replacing solar, but adding a reliable tool to our cosmic toolkit. For the moon, nuclear is a game-changer. It's the difference between surviving and thriving. With nuclear, we can build, explore, and stay for the long haul. That's why NASA is betting on the atom. The future of lunar power is nuclear. So what is nuclear fission power? It's simpler than it sounds. A reactor splits uranium atoms, releasing heat and more neutrons, triggering a chain reaction. This process generates a constant, powerful source of heat. The heat runs an engine. NASA plans to use a Stirling engine, which turns heat into electricity. The engine's pistons move back and forth, spinning a generator. The result? Reliable electrical power. Control is key. Engineers use rods that absorb neutrons to regulate the reaction. Insert the rods, slow the reaction, withdraw them, speed it up. This keeps the reactor safe and stable. The whole system is designed for efficiency and safety. It's a carefully balanced atomic dance. The goal: a safe, long-lasting power source for lunar explorers. With fission, we can power the moon for years. That's the promise of nuclear energy in space. NASA's not starting from scratch. They've already tested the tech. The Kilopower project proved a small, safe fission reactor could work for space missions. The crusty prototype ran flawlessly in desert tests, adjusting power automatically and staying safe. The core was tiny, but it produced enough power for a household kitchen. The goal: a system that runs for at least 10 years, powering life support and science gear for a lunar outpost. Kilopower's success gave NASA confidence to move forward. Now they're designing a flight-ready reactor for the moon. It's compact, self-regulating, and built to last. Soon, a small nuclear battery could power the first lunar base. The future of moon power is already taking shape. NASA knows it can't do this alone. In 2022, they teamed up with Lockheed Martin, Westinghouse, and Nine to design the next lunar reactors. Each company brings unique expertise: spacecraft, nuclear tech, and advanced engineering. The requirements: small, lightweight, and able to deliver 40 kilowatts for at least 10 years. That's enough to power dozens of homes. After a year of design, NASA will pick the best concepts to build and test. This partnership is key to the Artemis program and a new era of space-based nuclear power. The moon is just the beginning. Building a reactor is only half the battle. Designing it to withstand the harsh conditions of space and the moon is a monumental challenge in itself. Teams of engineers spend years perfecting every component, ensuring the reactor is compact, robust, and able to function flawlessly in the vacuum of space. But getting it to the moon is the real test. The journey from Earth to the lunar surface is fraught with risks, and every step must be meticulously planned. The reactor must survive the violent launch, enduring intense vibrations and G-forces, and arrive safely at its destination. It's launched cold and inert, completely shut down, with multiple layers of shielding and safety systems in place. No nuclear reaction takes place until it's securely on the moon, far from Earth and its inhabitants. This approach ensures maximum safety, even if something goes wrong during launch or transit. The reactor remains harmless, eliminating the risk of radioactive contamination. Once in lunar orbit, the lander must execute a precise, rocket-powered descent, navigating treacherous terrain and landing with pinpoint accuracy. The chosen landing site will be near the lunar South Pole, a region prized for its near-constant sunlight and potential water ice deposits. The reactor is placed well away from astronaut habitats and scientific equipment, ensuring safety and minimizing radiation exposure. After landing, the reactor is carefully deployed, either lowered directly to the surface or transported by a robotic rover to its final location. This step is critical, as the reactor must be positioned for optimal performance and safety, ready to power the lunar base. Only then is it activated. Control rods are withdrawn, the nuclear chain reaction begins, and for the first time, electricity flows from a nuclear plant on another world. It's a historic moment. Years of engineering, planning, and teamwork have led to this achievement. The journey is complex, filled with obstacles and innovation at every turn, but the payoff is huge. Reliable power will transform lunar exploration, enabling longer missions and more ambitious science. The moon will never be the same. With this technology, humanity takes a giant leap toward a permanent presence beyond Earth. With 40 kilowatts of steady power, the moon becomes a true outpost. Life support is reliable, no more rationing heat or air during the long night. Science flourishes, deep drilling, real-time analysis, and even 3D printing with lunar dust. Rovers can explore farther, and robots can build permanent structures. The reactor powers growth, turning survival into settlement. A robust power grid opens the door to industry and even tourism. Companies could plug into NASA's grid for mining or research. The reactor isn't just for NASA, it's the utility for the first lunar village. With nuclear power, the moon becomes a hub of science, industry, and human activity. The tiny atom powers our biggest dreams. The moon reactor is more than a lunar project, it's a test run for Mars. Mars is farther from the sun with weaker light and planet-wide dust storms. Solar panels won't cut it, nuclear is the answer. The tech we prove on the moon will power Mars missions and beyond. Nuclear rockets could cut travel time to Mars in half, making journeys safer and faster. For the outer planets, only nuclear can provide enough power. The small reactor on the moon is the dawn of the nuclear age in space. It's the key to unlocking the solar system. From the moon to Mars and beyond, nuclear power will take us there. The future of exploration is atomic, cosmic,